In this video, we will discuss a famous code forces problem that asks you to minimize the XOR between two elements of an array. You have to compute the solution in O of n log n time because the O of n square solution is the brute force one, which is very trivial. Now you might notice that I am calling this as a standard and famous code forces problem, although you might have never heard of it. And that's all right, because if you are a beginner or an intermediate competitive programmer, then every famous algorithm might not be known to you, but at some point in your journey you will learn about that technique for the first time. Maybe this video will act as the trigger point, after which you will always remember the solution to this particular problem. In fact, when I attended a code forces round and this problem appeared for the first time, not this exact problem, but uh, a derived problem that uses the ideas from the solution to this problem. When it came in the code forces round, then everyone in the comment section was like, this is a very standard techniques, everybody knows about it. And I was so confused, like, is there a secret code forces society or something where they are discussing these techniques, right? And then I realized that okay, it's all about having that experience, like solving that number of problems, that every hidden technique you can learn and then you can apply it to future problems. So for this particular problem is a bit interesting in the sense that in all of my videos, right, I guide you through the intuition of how we arrived at a particular solution. But this is one of those problems, well, where I'll not share the intuition behind the problem, behind the solution. Instead, I will prove why that is correct. And that is all right, because not everything can be arrived at by yourself. For example, consider the time complexity of binary search, right? Or consider the uh, time complexity of sorting an array. You know that the best we can do is n log n, right? Can you prove that the best that we can do is n log n? Yes, you can do that, because if you have taken an algorithms course, then your professor might have showed you the proof of why it is not possible to improve any sorting algorithm beyond O of n log n. But if you had not known this fact and I asked you to come up with the upper bound of sorting algorithm, then it's pretty hard to come up with, right? So this is just one of those facts that you look at it and then you convince yourself that it is correct, you prove that it is correct, and then you just live with it, right? So in similar veins, for this particular problem, I'll directly jump onto the solution. So the solution is this. The answer is that everyone on code forces knows that if you want to compute the minimum XOR between two elements of an array, you have to sort the array first, and then the minimum XOR will be present either here, this one, or this one, or this one, or this one. Basically, it will always be between consecutive elements of the sorted array. So that is it. That is the entire algorithm, right? In the remainder of the video, I will prove why this is correct, right? But we will not talk about idea of how did we even arrive at this conclusion. Okay, so this is just a fact that you can take for granted. But if you have a beautiful and elegant intuition behind reaching this like conclusion, right, without like using anything, or just reaching this conclusion from scratch, do let me know in the comment section. I'd be happy to pin that comment. But so far I have not found anything that could convince me that I could naturally arrive at this solution by myself, right? Maybe some people might. So, and that's fine, right? Like even if you take away this point from this video, that the minimum XOR will always be between some consecutive elements in the sorted array, that serves the purpose of this video. So now let's talk about the proof of why this statement is correct, right? But before we do that, right, let me see how correct is this statement is in general, right? So what does this statement suggest? So it says that minimum XOR is always between consecutive elements in the sorted array. So this might give you a false idea that consecutive elements in the sorted array means something like 2, 3, 8, 12, 15, etc. So if it is saying that it is minimum XOR is always between consecutive elements in the sorted array, then you might think that, okay, if you have two numbers a and b and you have their XOR, like let's say a XOR b, and then if you increase the gap between a and b, and like suppose b is over here, then if you increase the gap, then the XOR also increases, right? This is the first conclusion that you might make after looking at this statement. This is one of the generalizations that you might make, but this generalization is actually incorrect. That is, increasing the gap between the numbers does not increase the XOR. So I will show you a counter example of why that is correct, or false. Okay, so let's see. So consider 2 XOR 4. Okay, so what is the binary representation of 2? It is 1 and 0. And what is the binary representation of 4? It is 1, 0, 0. So what is the XOR between 2 and 4? It is 1, 1, 0, which is 6. Now, what if you increase the gap between 2 and 4? Right now the gap is 2. What if you increase the gap? So you make it 2 and you move 4 further down and make it as 6, right? So if you see, binary representation of 2 is 1, 0, and binary representation of 6 is 1, 1, 0. Now if you take the XOR between them, you will see that the answer is 0, 0, 1, which is 4. So you can see that the gap increased, but the XOR decreased. So the statement that you see on the screen is correct. But if you try to generalize it, then all of those are not correct. That is, if this is the gap between two numbers and it forms some XOR x, then if you increase the gap between these numbers and it forms a XOR y, then you cannot say for sure which one will be greater, x or y. But this statement still says that XOR will always be present between consecutive elements, right? So now let's prove this. Okay, so we are trying to prove this particular statement. And how do we do that? So suppose we have an element A and an element C, and these are the elements that produce the final XOR. So A XOR C is minimal. Then this statement claims that it has to be some consecutive elements, right? Now to contradict this, right, or to prove it otherwise, let's assume that there is some element in between, like these are not, A and C are not consecutive. There is at least one element in between them in a sorted in the sorted array, right? Note that this B, right, A is also present in the array, B is also present in the array, C is also present in the array. This is one of the important thing, like I should mention, like A, B, C are present in the array, are present. Okay, and assume that A XOR C is producing the minimal XOR. Now, if A XOR C is producing the minimal XOR, then let's look at the bitwise representation of A XOR C. Then it will be something like it will have some leading zeros, and after that it will have 1 at some point, and then it will have something, right? We don't know what. So let's focus on this particular bit position. The first time 1 appears from the left for A XOR C. So if it is 1, right, it means that XOR equal to 1 implies a bit difference, that is 0 XOR 1 is 1 and 1 XOR 0 is 1, right? Otherwise, if the bits are identical, then this could have never been 1. So if this is actually 1, right, this means that one of this is 0 at this bit index and the other is 1, right? Now, if I say that A is less than C, right, what does this statement mean? This means that A and C, they will share a common prefix of that bitwise representation, which will be mostly 0 0 0, then 1 0 1 0, etc. And then C will also have this representation 1 0 1 0 0, and at some point, so C is the higher number, right? So at some point C will be 1 and then A will be 0, right? This is the first bit position that they will differ, right? And after you have set this leading bit as 0, then you are free to set any of the bits over here. This is A and this is C, right? So after you have set the highest order bit, like after the highest order bit has mismatched, right, it is 1 and this has become 0, then you are free to set any of these bits to either 0 or 1, and this resulting number, right, this will always be smaller than C. Why is that true? Because the sum of all of these lower order bits, it is nothing but 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, etc., up to 2 to the power, let's say this is index I, right? So up to 2 to the power I minus 1. And from your number theory class, you know that this sum is equal to 2 to the power I minus 1. This means that no matter what these bits uh, do together, even if they all of them combine, they can never reach the strength of 2 to the power I, right? They are one short. This means that if this bit is unset, then no matter what you do with this smaller number will always be smaller than this. A will always be smaller than C. So, and the position where this first bit difference happened, that is the point where the XOR will have 1 in its place. So this means that if it has 1, then for sure C would have had a 1 over there and A would have had 0, right? So now let me again go to a different page and let's recap what we have concluded so far. So assume you have B in between and this is C, and you are claiming that A XOR C produces the minimal output even when A XOR B was a possibility and B XOR C was a possibility, but you are claiming that A XOR C is the minimal output, right? And what we are looking at is the binary representation of A XOR C, and we said that it will contain some zeros and at some point it will contain 1, and then after that it can contain anything, and we are claiming that the point at which A XOR C contains 1, then at this index I, C will have a set bit, C will have 1 and A will have 0. Now pause this video and convince yourself why this fact is true. Why C will have a 1 and A will have a 0. This is compulsory. So if C has a 1 and A will have a 0, then if B is sandwiched between A and C, then you can notice that, so if B is less than C, right? If B is less than C and A is less than B, right? Then what can the bit value of the bit at index I for the element B be, right? For example, it can either be, so it has two choices, right? It can either be it can either be 0 or 1. Now, if the bit at index I for element B, if it is 0, right? If it is 0, then you could have done A's or B and A's or B, right? Both of them contain 0 and 0 at bit position I, right? Then the resulting XOR will not have this set bit anymore. So of course this A or B is smaller than A or C. Why? Because their highest order bit does not match, right? So highest order bit is unset in A or B. But if B had a 1 in its place, right, at the bit index I, if B had a 1, then you can see that B is or C. So if B had a 1 at index I, right, if it had a 1, and C also had a 1, that part we are sure about, then if you XOR them, then the bit at index I would vanish, right? So index I, so this will vanish, and in both of the cases we have proved that it is always possible to unset the first set bit of A or C by selecting a number in between if you have that available. And if in case it was not clear to you, like why are we only focusing on the bit at bit position I, and why do we not care about the bits on the left hand side, like why can't they increase, right? Like if you switch to A's or B, or if you switch to B's or C, is there not a possibility that these unset bits could become 1 and then this number itself becomes bigger? So that is actually not a possibility, because we already concluded that A and C share these many similar bits between them. So if they do, then anything that is sandwiched in between, they also have to share the same number of leading bits, right? So this is the general general ordering of binary representation. I, I will not dive deep into that. But if you are confused on that part, on why we need to focus on the ith bit, maybe you should take some time to figure out like what this expression implies, right? If you have this expression, and if you have already concluded that A and C share a common prefix, and then diverges on a suffix, then it is guaranteed that B will also share that prefix. Okay, so try to prove that by yourself. So we have shown that if there is a number that is in between that is available, then XOR will always become smaller by either switching to the left hand side or to the right hand side, right? Depending upon which one has a 0 and which one has a 1. And in this manner, we have proved that minimum XOR, will always be produced by some consecutive elements of the sorted array, right? Now you can notice like what was the difference between this statement and the general gap statement, right? So that general gap statement, that was assuming that you have so that general gap statement, right, there you did not have fixed numbers, right? You are talking about any random two numbers, right? But here we are saying that this B, right, this B has to be present in the array. If it is there in the array, only then it will be minimized, like if you select A and B, or B and C. But if it is missing, like if there is nothing, then of course A and C are already in between, right? So yeah, I hope you understood the idea, and let me also walk you through a sample, like maybe an example through which you can understand this abstract idea better, like this ordering that we have defined, right? A, B, and C. So let's look at a concrete example. So suppose we take A as 1 1 0 0 0 1 1 1. Now let me take B as, or in fact even before taking B, right? Let me take C as 1 1 1 0 0 1 1 1. Now what would their XOR be? So you can notice that A XOR C is equal to 0 0 1 0 0 0 0 0. Now you can notice that the first set bit in A XOR C is the position where the prefix stopped being identical. And here you can notice that C was the bigger number, so that's why it had the this bit set, and A was the smaller number. So at this point, right, anything that is smaller than C but greater than A, they will also have to share this prefix, right? So then if B has 1 over here in this set bit, then we can just switch to B XOR C to get a smaller XOR. But if B has 0 in that bit, then we can switch to A XOR B. And that's how we have the conclusion again of this video, is that minimum XOR will always be between consecutive elements in a sorted order. So you can remember this as a fact. Now maybe in the next video we'll discuss an application of this problem, because that is exactly what you can use it for, because it is almost impossible that you'll receive an exact problem in future code forces round that asks you to compute the minimums or between two elements. But some of the problems might involve some application of this. Okay, so you can, I'll try to add another video that uses this fact to solve a complex problem. But if you want, you can even try to solve that problem by yourself. The name of the problem is binary spiders on code forces. So this is one problem that uses this fact, right? And if you look into the comment section of this particular editorial for this problem, you'll see everyone talking about that. Everyone knows that XOR is always minimized between consecutive elements of a sorted array. But I did not know that, and I hope that now you know. And now you so even though it was not possible to come up with this fact all by yourself, but I hope that the proof that I presented was easy enough for you. And maybe it sounds a bit convoluted when you like just view the video, okay, but when you actually try to sit down and write some equations, write some zeros and ones, maybe that might clear things for you. And yeah, let me know in the comment section if you have any questions regarding this, like if something is not clear, or if you have some more practice problems that you want to share with others. Let me know in the comment sections. Thank you.